and in the different potential ways that we could represent a drawing of methane. So one of the big things that's going to come out of your drawings for methane is our standard default for all carbons, for all sp3 carbons, would be that we're always going to have two solid lines. We'll have one wedge and we'll have one dash. The wedge and the dash are sometimes optionally included. There doesn't have to be a reason for showing them, but there usually is some kind of reason for it. So the reason why it's being shown here is I'm trying to emphasize the fact that I have a hydrogen coming out of the board and a hydrogen going away. Okay, so it's just kind of a visual aid in this case. Okay, but that's not a super good reason for it, because sometimes we just don't need that visual aid. So when we move into chapter 5, we'll find out there's a legitimate reason for showing it. We aren't quite there yet, so don't stress exactly. Okay? So every time you draw an sp3 carbon, you should be thinking about the two solid, the one wedge, and the one dash. Again, sometimes it's more important than others to go through and show it. Okay? If we went through and did ethane, well, I thought I had a nice Lewis structure drawn there. So we'll draw that up at the top. If we drew out ethane as a Lewis structure, we could draw this. Okay. What is the hybridization of each of those carbons? sp3, okay, with a tetrahedral shape, which means really we should be drawing those with wedges and dashes. Okay, so there is the option to draw it kind of like this, wedge dash, or we could have drawn it with the wedge dash kind of up and the hydrogen down. Does this change the identity of ethane? No. Okay, so we might say, well, who cares? Why should I draw one over the other? Okay, because they're freely allowed to interconvert between each other because of the sigma bond overlap there. It doesn't change when I rotate, that it doesn't really matter which one I draw. Unfortunately, that's not true. One of those ends up being better than the other, but our VSEPR drawing doesn't show that very well. What we would have to do is scaffold out to a larger, or the actual molecule, to try and get some idea of why it might be important. Okay? So if we really quickly do that, theoretically really quickly do that, ignore the colors. Right, the structure on the left is being shown with this model. Notice we've got our hydrogens going up in the same plane of the paper as our carbon connection. We have two atoms that are coming towards you, two atoms going away. The other option, sorry, make sure I do this right, would be if I did that sigma rotation, I grab the right-hand one. So I got that hydrogen going up, the hydrogen going down in the plane of the paper. So it's not much of a difference. Right? However, if we change our view on the molecule, like that, well, it still doesn't make a difference. We're still looking at it from the side. But what happens if we turn and look at it from the end? Well, in this viewpoint, our drawing now looks inherently different. One of the big things that comes out of this is if we're looking at this right, the carbon-carbon bond that connects those disappears from view. Right? So if we go through back to our original, so there's our rightmost drawing. Okay, so what I've done is taken that rightmost, or the rightmost drawing, I took the left carbon and I folded backwards. What I'm now showing is roughly what the textbook image is trying to show down here. Everybody kind of see that? So they kind of tilted it. Right. If we full on drop that down so we can't see that second bond, and we now rotate. Well, that was a tiny little degree to rotate. I think 60 degrees. Okay. Does that change anything about the structure? Right? It is still ethane, but what happened to the bonds now? They're now all overlapping each other, so we can't see them. Kind of like if the Earth eclipsed the sun and we saw a solar eclipse, right? Okay, we've hidden some pieces. Right? Or if we did that rotation back to where it was, well, now all of those bonds are visible, again, except for that carbon-carbon bond. Well, now they aren't eclipsed. Those bonds are staggered away from each other. Right? Well, are those different? Okay? Again, it's the same atom or same molecule, so we can't really say they're different. Okay? But is there something different about them? Well, we draw them differently. Okay? But is that important? Okay? Turns out that it's energetically a big deal. Each of those bonds represents what? A pair of electrons. Right? And what do electrons want to do?
Be as far away as possible.
Be as far away as possible from
Each other.
other electrons. If we look at the eclipsed view, the electrons in the bond to that front atom are in the same plane as the electrons in the back. Which means the electrons have less space. They can't kind of spread out along that axis because there's other electrons in the way. Okay? We've closed off space for them. If we do the rotation back, now the electrons on that front bond could slide all the way backwards because there's no electrons there. We've increased the space theoretically for them to move. They become lower in energy. So what we're talking about here are now what are known as conformational isomers. And it generates different structures or different energies. Okay? And that all has to do with the rotation of that sigma bond, which is an interesting kind of question to draw in. Do I need to worry about that issue with, say, alkenes? What is an alkene? It's a sigma and a pi. Can I rotate the pi? No. So this rotational issue doesn't show up with pi bonds. So alkenes and alkynes, double and triple bonds, we don't have to worry about this for because they can't rotate about that carbon-carbon single bond. It's only when it's a single bond that I have to worry about this. Okay? And this is where I introduce this concept. Okay? Well, we've looked at it from the side, and we just called that line angle. Okay? We added wedges and dashes, and we called it Vesper. Okay? And we said we didn't really need another way to do it, right? Because this way is the best way to look at it from the side because I see all the bonds. And then some jackhole comes through and says, well, if you turn it so that you can't see one of those bonds, you can actually tell a difference between those rotations. You go, oh, crap, well, I guess you're right. Because I said that it wasn't important and you proved me wrong, I'm now going to forever acknowledge how superior your intellect was to mine and associate your name with having found that viewpoint on the molecule. That's where we end up with what is known as the Newman projections. Okay? So it's a switch on our viewpoint for the molecule. Okay? Again, does it change the identity of the compound? No. The identity of the compound stays the same, but I can now evaluate something about the energy of individual positions or rotations of those pieces. Right? Well, this is never relevant in the human world because humans don't have higher and lower energies states for their rotations. How many of you, when you walk on your hands? Why not?
It's hard to do.
That's hard to do. Okay? So how we interact with the world changes based on our energy states. Same thing happens with our molecules. Okay? So we have to be aware of those rotations. However, if all of a sudden I started walking on my hands, I can't. Okay? But if I started doing it, does that change the identity of who I am? I might be cooler because I could do it, but I'd still be Mike. So if you saw me walking on my hands versus on my feet, you would still have to acknowledge me as the same person. You're aware of all of those possible states because you can see me. You can identify those aspects. Why does this become problematic with OChem? Can we see any of these molecules? No. All we can do is mimic how they look by using the model kits, okay? Or be really good about seeing things in 3 dimensions. Okay? Most people are not good at 3 dimensions, which is why you need the model kits, because you need to be aware of all of the possible permutations of how you could draw that molecule, be it on its head, be it rotated, be it standing. You have to acknowledge that all of those things are the same. And that's where we encounter our beginning of our flow chart for identifying the relationship between molecules. Okay, so for any 2 molecules, we would move through this flow chart and just evaluate. What are we looking at? If they have the same or different molecular formulas, well, then they're different. Right? That's the definition of different. What if they have the same molecular formula? When we move through to the yes category, we're left with the exact same answer we started with, A and B. We can't differentiate them. Okay? Until we move to the next question. Are they superimposable? So if they are superimposable, then I can say those 2 molecules are identical to each other. If they're not, now they're isomers. Cool, so we could say, well, there's only 3 definitions I need to worry about, except isomers can subcategorize, okay, into the atom connectivity, into structural isomers and stereoisomers. So we have to be able to look at those molecules and evaluate what we have. So let's take a look at the top, just to get an idea of what's happening here. Let's take a look at those top 2. The first question we would ask is, do they have the same molecular formula? Right? And this is where people could go through and be like, well, 1, 2, 3, 4. Well, there's 5 carbons. That has 3 hydrogens. That has 1. That has 2. That has 3. That has 3. So that was 3, 6, 9, H12. Then I move to the next one. C5H 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, H12. And some people might be saying, well, yeah, that's exactly what I do. You just took a minute to answer a question that needed to happen in less than 2 seconds. Okay? How do you get that familiarity? Practice. This is why you draw Lewis structures. This is why you build from that. This is why you have to start doing that practice to internalize those relationships, to find those formulas almost instantaneously, to recognize those have the same formula. Right? Because they have the same formula, we could then jump down to then saying, are they then superimposable? Okay? So we would try and overlay those, and we would find we can't superimpose them. That makes them isomers. We would then move to the atom connectivity, which usually throws people for a loop, okay, on trying to figure out what that then means. Okay, the easiest way that I would go through and look at this, well, there's 2 ways, actually. 1, name the compounds. If they have the same name, at least at this stage, then do they have the same atom connectivity? Yes. If they have different names, then no, they're structural isomers. Okay? How many of you can name those compounds now? What's the first one? Took too long. Sorry. That's where I was aiming for. We need a speed behind doing that nomenclature, which again comes to practice. Okay? And everyone goes, well, speed isn't a big deal. Why do you have to test on speed? Go to your doctor the next time you're sick. If the doctor turned around and said, I will cure you, I will fix your illness, but call me again in a month and I'll let you know what to do. Okay, you're probably never going to go to that doctor again. But if you called him again in a month, you were probably cured. Right? You probably didn't have that issue anymore because it was probably like a flu, something like that. But you go to another doctor, and that day they're like, here, take these pills. You'll probably go back to that doctor. Does speed matter? Yes. Speed is hugely important. Unfortunately, that is part of the real world. We have to be tested on speed. It's going to happen. Okay? So, if you can't do nomenclature that fast, we need to come up with another way to evaluate our atom connectivity. So find similarities. I see 4 carbons in a chain. I see 4 carbons in a chain. Each of them have one extra piece. Is that one extra piece connected to the same carbon? No. Atom connectivity has changed. I don't have to name it. I've just acknowledged that that piece is somewhere else. So you find similarities between the structures and move on. Okay? So the top 2 are structural isomers. Okay? How about the bottom 2? Do they have the same molecular formula? Yes. Okay. Are they superimposable? Usually that causes some trip-ups, because what people do is they go through and look at it and they say, well, in one case, there's my structure. The other case was that one. I can't overlay those. Those don't superimpose on each other. The carbons are aimed different directions. That doesn't work. For the drawing, yes. For the molecule, all I did was a sigma bond rotation. Am I allowed to rotate? Yes. Does that change the identity of the compound? No. Are they superimposable?
Yes.
Yes. The relationship between those two is that they are identical. Okay. That is hard, particularly for people that don't use model kits, because they don't acknowledge that spatial reasoning yet. Use the model kit. For those of you in lab on Monday, how exciting is playing with those model kits? Yay! Everybody on Wednesday, I'm sure, can come back and tell me on Monday how great and exciting it was, and how many times you wanted to punch me in the face. Why are you making me do this? This is why. Okay? I will accept that. Get mad at me, get it right. Okay? You don't have to like me if you get it right. Right? So we have to move through our flowchart and see those relationships and recognize that we have that free rotation. It will make our structures look different in a drawing. You are responsible for acknowledging that outside of the drawing they have free rotation and free motion. That doesn't change their identity. Okay? That would be a weird world. Every time I moved my arm, you'd have to call me something else. Right? You'd probably run out of 4-letter words really quickly. Ethane drawings. Okay, if we looked at ethane, we could look at our Lewis structure, we could look at our line angle, okay, which we've seen. In this view, remember we said we're now changing our viewpoint on the molecule, we're looking at it on the end. So usually you see this representation with an eyeball, looking at it from the side. So in this case, I'm trying to provide that context of what do you see? Where's the angle that you are looking at when you evaluate this structure? When we go through and do that, we're going to have to redraw our image because we're changing our viewpoint. What you should end up drawing would be something along these lines. Notice the bottom one, or bottom left. Didn't the bonds overlap each other? So you wouldn't be able to see the atom behind, right? But if I had just drawn something like this, well, that's the wrong button. So let's try that again. Come on, work with me. Thank you. If I had just drawn this, we've been like, well, I have no idea what you're drawing. Okay. I drew everything on top of each other. Okay. It's relatively straightforward if they're all hydrogens, but what if one of them is a carbon? Is that carbon attached to the front carbon or the back carbon? Well, I got no freaking clue because you drew them all on top of each other. Okay. So in that form where they are now overlapping, we stagger them slightly so that we can see where they're connected. Okay. And we encounter some issues here. We've got this large circle in back, and then we have this point in front. If we looked at that model, which atom would you expect to be the large atom, the large circle? Probably the one in the front, right? You can't see the one in the back. Okay? But if you can't see the one in the back, would you be able to show what the bonds were connected to? No. So we do a reverse perspective on our Newman projection. The back atom gets the large circle, the front atom gets a point. Okay? We will then draw where the bonds are with respect to that atom. If we do the rotation, we would then do the same deal. Large atom, circle in the back, what things are connected to it, what things are connected to the one in front. Okay? Notice the shapes coming after that. Those bond angles end up appearing to be 120 degrees, right? Everybody agree with that statement?
Yes.
Okay, then I'm not even going to challenge that. That's just what it looks like. Okay? And this is now a Newman projection. So I want to go through and name these as different things because they have different energies. The one on the left is higher in energy because the electrons are all in the same plane. The other one is lower in energy because the electrons are not all in the same plane. They're all in the same plane, eclipsed. Out of the plane, staggered. Okay? Yes?
How do you identify the carbon in the back?
What if it's a different element?
How's that?
Do we have a way to do that with this drawing? No, we don't. Okay? So what we would have to do is add some extra context into what we were drawing and say, well, the back atom is a nitrogen. Now you're looking at that. You would still have to draw it as a circle to see this. Okay? Typically, when you're looking at Newman projections, they're only carbons. I can only think of one case where I've ever seen a Newman projection that wasn't carbons in both cases, and that was my fault. Okay? Biochemistry. Okay? So we can do it, we just have to add that extra context. Okay? So that was ethane. Now we move on theoretically to the third one, which would be propane. But I'm going to skip propane because that doesn't really add any new flavor or nuance to our discussion. But if we go through and do butane in particular, actually never mind, just butane. So we're looking at the straight chain carbon process. And we want to consider our Newman projection again. Well, the Newman projection sights down a carbon-carbon bond. Why would butane potentially be a little bit more challenging than ethane? There's multiple carbon-carbon bonds to look down. Okay? Only one of them becomes particularly relevant. That is the carbon-2, carbon-3 bond. Okay? Seeing some faces about that. How do I know one is carbon-2 and the other one's carbon-3? I could go through and label them 1, 2, 3, 4. Why did I not label them 1, 2, 3, 4? Nomenclature. Go in sequence. That's where it's coming from. Whoa, that was also not the right button. Okay, so if you went and looked down the 2,3 bond, what would you see? Okay. Take a minute and draw it. As if people will go through and be like, well, I don't need to draw it. I don't need to look at the models. Because when I read the textbook said it looked like that. So now I know the answer. Of course you freaking do. You saw the answer. Okay? That doesn't mean you understand it. Okay? You have to be able to understand what you're looking at. That's why you use the model kit. That's why you visualize it. That's why you see it. Otherwise, you're memorizing it. And when people freak out and go, oh God, there's so much memorization, that's because you didn't spend any of the time to actually learn the material. Okay? You just tried to memorize the answer. Okay? If I ask butane, guess what happens? Great, you memorize the answer. I ask pentane. You're up not a pleasant creek without a paddle, because you now have no concept of how to manipulate or change the structures because you haven't worked with those models. You haven't picked up that three-dimensional characteristics. Okay? Looking at the answer is great for knowing the answer. That's why the kind of odd timing. You looked at the answer. It tells you the answer. The exam doesn't tell you the answer. When we go through and look at butane, what you'll notice is that you will end up with several structures, okay, where those X's would be CH3s. you should end up with two, interestingly, new staggered positions and two new eclipsed positions. All right? So you'll end up with four possible orientations, as opposed to just the two that we had for ethane. Okay? Well, but they're staggered, so who cares? They've got to be the same. Okay? Well, what is different between butane and ethane?
Butane has carbons.
Butane has carbons. Well, why is carbon different than hydrogen?
It has 4 hydrogens attached to it.
Hydrogen has less electrons than carbon. And what were we talking about when looking at the Newman projection? The electrons occupying a space. If carbon has more electrons, is that going to generate a different relationship than if it was hydrogen?
Yes.
Yes. Okay. That different relationship applies to both the staggered and the eclipsed. The eclipsed relationships we tend to ignore. We ignore them because they are energy maximums, much like a transition state. The only thing we do with a transition state is say it's there, and that's about it. Okay? We try to avoid any other assessment there because what ends up happening is if we assign too much weight to it, we start to make the assumption that the transition state exists. Does the transition state exist? That's a fun 152 question. No, it doesn't exist. The transition state is by definition the transition between one species and another. Okay? It doesn't actually have an existence. It's just the motion between those 2 points. Okay? Same thing for our eclipsed. It is a transition state as we move to each of the staggered conformations. If we look at the 2 staggered conformations that we have drawn up here, would I expect them to be of equal energy? No. Which one would I expect to be higher in energy? Why would the left one be higher in energy than the right? Those carbons with more electrons than hydrogen are closer to each other than the carbons in the other situation. They're as far away from each other as we can possibly get. So we have a difference. And when we have a difference, what do we then have to do? I'm Mike, you're Bob. We have to name them. What do we name them? Okay. I would pick the rightmost one as the easiest to name. They're on opposite sides of each other, right? So they're kind of like anti each other. Yeah, that makes sense. And these are kind of like close to each other. So I'll call those gauche, because that makes a lot of sense. What is the gauche from? French. Is French for awkward? Really?
The book said. I think of it like standing in
Oh,
a
that's cool.
urinal. You don't want to stand too close to somebody. Not like I've ever stood in a urinal.
So you've heard. That makes sense. I kind of like that one. I like that analogy. I'm going to have to keep using that. Okay. If these are now people at a urinal, you want a little bit of space there. It's one of those kind of unwritten man laws, right? When you walk into the bathroom, you see someone, you don't stand next to them. You definitely don't share. You don't share. That's like really bad. Okay? But you don't want to be like right next to them. You want to give them a little privacy. You want a little privacy, so you space out a little bit. You go into the anti. So the gauche works out as like the awkward. You're standing there using the urinal, and the guy comes up and stands right next to you. And then turns and stares you in the eye. Like, yeah, I'm just trying to, evacuate my intestinal system. Remember how we talked about intestines when we introduced each other? What do? Handshake. Oh, I did this in Gen Chem. We do a handshake, right? We don't be like, here's my stomach. You walk up the very first time you meet someone, and they're like, you're like, whoa, stop sharing. Okay? We start slowly. Okay? Give that space, that's now a lower energy state. Get too close, that's a little awkward, that's a higher energy state. While that is higher in energy, it is not as high as the eclipsed. Okay? They're like standing behind you trying to pee over your shoulder. Okay. So, what does this then translate to as far as energy? Sorry, I went way too far. I apologize. At least I didn't record that. I did. Let's start at our eclipsed. Is the eclipsed higher or lower in energy than the one next to it? Higher in energy. So I'm gonna just put a dot. Okay, I'm just gonna say it's here. And the next one is lower in energy, right? So I'm gonna put it there. How about the next one? Okay. What are we comparing it to? That's always a good question. I want to compare it to the closest thing to it. How about what's immediately in front of it? I'll pair it one back to the gouache. The eclipsed is higher in energy than the gouache? Yeah, I actually said higher, didn't I? I meant to say lower. The eclipsed is higher in energy than the gouache. What was the first one? Also eclipsed, which was? Higher in energy than the gouache. So as soon as I move to eclipsed, it should be higher in energy. But we had an interesting point. So it is higher than the gouache, but is it higher than the totally eclipsed? Why not? Because one is totally. No, come on. I'm looking at a carbon seeing a hydrogen versus a carbon seeing a carbon. Okay? What's the difference between carbon and hydrogen? Carbon has more electrons. Okay? So I would expect that to be higher than energy than the gouache, but not as high energy as the other one. How about the next rotation? That should now be lower in energy than the eclipse. Should it be lower in energy than the gouache? Yes. Next one. Higher in energy than the anti. Should it be higher in energy than our red underlined eclipsed? They're the same. Okay? They're just on different sides of the structure, but the energy is the same. The next one. Okay. So we've now just marked lines on this. Okay? All that's happened is I've done a rotation. So this is a smooth transition. If I want to now connect all of these, those of you connect the dots like we just do that. That looks ugly and awful and horrible, so we don't do that. We do nice smooth lines, right? And what does it look like we've started to draw? We could go through a wave. I'd accept that. What if I put an R here, a double dagger there, a P there? Seriously, you guys can't answer that question? That's okay. What did we just draw? Wow, I need to talk to the 152 instructors. This is an energy diagram. This is the energy required to run a reaction. I have R for reactants, P for products. Everything you did in 152 was this. All those calculations was this. It was defining where each of those points were. Yeah. Every single thing you did in 152 was looking at that. Okay. So what have we done? We've now generated an energy diagram for the rotation about the sigma bond in butane. Remember how I said the eclipsed, a little bit less important? I mean, we could call them totally eclipsed versus eclipsed. That starts to bring in too many songs that we don't want to worry about. That's, painful memories. Okay. Why do I not care about the eclipsed? It's at a peak. It's at the transition between those wells. Remember I always said it's a transition state? Okay? That's what's happening. It doesn't actually exist. It doesn't belong anywhere. What we're concerned about is the wells, because those wells are where my chemistry is going to happen, because that's where the molecule exists. Okay? So we have energy diagrams that can relate to these things. Will we see energy diagrams again? Yes. Okay? And in fact, that's one of the reasons why I like our textbook, is we look at a lot of energy diagrams. Okay? They drew it prettier. Okay? Notice also they've specified a bunch of numbers in here. What are those numbers? Those are actual energies. In the drawing that I had, did you see any actual energies? No, why not? Because I don't care. I can't do math. Okay? We could do math. That's fine. We could do that. That's 152. Or that's a physical organic chemist. Okay? I'm not a physical organic chemist. I'm a chemical organic chemist. Again, wrong class. As we continue to add carbons in a chain, we don't see anything particularly exciting happen. Okay? So butane, pentane, hexane are all going to end up with the same kind of systems that come out of it with our Newman projections. Okay? The rest of chapter 4 goes back and looks at cycloalkanes. What happens if instead of these being in a chain, I loop them back on themselves? Okay? Well, in the nomenclature, I have to include the word cyclo so that I know that's what I'm supposed to be doing. Okay? So when you see cyclo, loop it. When you see cycloheptane, that's usually a question that I would skip. Any ideas why? How do you draw a cycloheptane? Okay. For those of you being like, it's just 7 points. Yeah, do it. Okay. It's not easy. It's really, really hard to draw. Ooh, that's actually a good point. I want to see that. Okay. A lot of people complain, oh, you should just give me handouts that shows all those cyclohexanes because you draw them so much better than me. It's because I've been drawing them for 15 freaking years. Okay. I put in the time, you put in the time. Okay. If you don't want to put in the time, there's little stencils. You could just buy the thing that has little stencils and then just real quickly draw them. That works. Okay? This stencil is extra cool because it has these shapes in the upper right-hand corner that is now becoming left. But the upper right-hand corner and officially the upper left-hand corner, those are some interesting, weird-looking shapes. Okay? Those interesting-looking shapes become a pain to draw for most students. If you got a stencil, you don't have to worry about how to draw them. The stencil does it for you. Okay. Don't want to buy a stencil? How much does that one cost, if you don't mind me asking?
Off Amazon 14.
Yeah, that's... What I've heard is it's like $15.
It's the cheapest.
It depends on different people's perspective. I would argue that's more money than I want to spend.
Are we allowed to use that on the test?
Yeah, absolutely. There's nothing wrong with using... It's a ruler.
I know.
I'm fine with you using a ruler. That's okay. Right? So, when we move into our cycloalkanes, we need to get used to dealing with these shapes and some of the properties that come with them. You should be able to draw a triangle and a square pretty easily. The cyclopentane, you'll probably do okay at. The cyclohexane, you'll get good at least by the end of second semester, because we spent an entire chapter looking at the reactivity of cyclohexane-ish type structures. Cycloheptanes, no one ever knows how to draw. That's just the life. Okay? Are there things that we need to be concerned about, like energy considerations? Yes. Hybridization, bond angles, Newman projections, rotations, are all of these things that we need to now stack into these new structures? Yes. Did we already talk about all of those things? Yes. So there's nothing new for me to talk about. I can just skip the next 20 slides and we can just jump straight to the test. Okay. All we're looking at is now practicing those same concepts. We do the same thing again and again and again. Okay? Let's look at hybridization. What is the hybridization of every single carbon drawn up there? sp3. What is the bond angle for an... let's take a step back from that. What is the shape for an sp3 carbon? Tetrahedral. What kind of bond angle should you have? 109.5. That's all the electrons getting as far away from each other as possible. Does the structure of a cyclostructure prevent that? Yes. I can't possibly fit 3 carbons next to each other with a 109-degree angle between them and have them connect to each other with the same bond lengths. So what happens? To generate that structure, I must take those carbons and fold them in tight to each other to make that bond. Is that an easy thing to do? I thought I could do it. Ah! Boom! It's made. If you have the gray box kit, great. Make a cyclopropane. See how horribly painful it is. If you have the Darling model, do not do it for your life. You will break the model kit. Okay? That is how difficult it is to make a cyclopropane. The bond angle within that is 60 degrees. You're taking something that wants to be roughly 110 and making it 60. Right? That's not an easy thing. Which means what happens with cyclopropanes? A lot of strain, which then means high energy. Right? They have a higher probability of breaking than, say, any of the others. What happens with a butane? Right, now it's 90 degrees as opposed to 60. Is that a little bit easier?
Yes.
My hand actually does not physically hurt by doing that. Okay? That's significantly easier. Right? If I add a 5th one in, is that easier? 6th, 7th, 8th. Right? By increasing the carbons, I can make that easier and I can reduce a lot of that bond angle strain. Okay? One of the kind of interesting features we find is that we go down in energy as we add carbons. Mike, you just said that. I did. We go down in energy to cyclohexane. Then what happens? We start going up. Why would it start to go up? The rotation that is now possible with the cycloheptane, okay, that rotation introduces more strain within the molecule. There's an extra kind of motion associated with it. When you go up to octane, same deal. There's more rotation in that. It goes to higher energy states. It never reaches the heights of cyclopropane, but it does go higher in energy. Right? If we consider, I had to broken that propane again. I said Newman projections, right? It's everybody's favorite. You guys now perfectly understand Newman projections. God, I'm sure the recording on this is awesome. We're just building a model kit, I swear. Adding that in that statement was not a good thing to add. Thankfully, you were far enough away. Okay? If I look at a Newman projection, what do you see?
Two carbons? 3 carbons.
They're eclipsed. What does that mean? Also makes cyclopropane a crap structure. We have eclipsed bonds. That increases the energy. Cyclopropane actually doesn't like that, so it officially is not fully eclipsed. It tweaks ever so slightly, and the bonds end up coming slightly out of alignment. Right? Don't stress on that, but it does. What happens when we move to butane? Where'd my bond go? Oh, I knew it. What happens when I go to butane? What happens to that projection? It still looks pretty eclipsed, right? Butane has a slight, little bit more rotation, and it comes slightly out of eclipsed. Not perfect, but it comes slightly out. If we jump up to pentane, guess what happens? It becomes even less eclipsed. Right? How does it become less eclipsed? It puckers the structure. And instead of being a nice flat structure that we saw with all the other ones, if we look at it from the side, are all those atoms in the exact same plane? No, we have what is known as the envelope. We have the 4 atoms in the same plane, and then we have the little flap. You look at the little flap and you fold it over, like snail mail. There you go. We have the envelope conformation. What happens when we add yet another carbon? Okay. Interesting thing with the other carbon before we look at the Newman projection. Anybody notice an extra feature here? I can get a lot more rotation.
The chair.
Each of those sigma bonds can freely rotate. Those people on Monday, or people that may have read ahead, are like, you have a chair. Actually, at no point did I have a chair because of how I was moving it. Okay? I have a boat. Okay? Is that a legitimate way to describe it? It's as legitimate as saying trigonal bipyramidal. Yes. It is a way of describing the shape that we see. We also have the chair. For those people on Wednesday that have no idea what we're talking about with a chair, or that aren't in lab, you should probably talk with me to make sure that you know what a chair looks like. Okay? So that you can find it, because that is a chair, believe it or not. Okay? The important part behind this, remember that Newman projection? What kind of conformation do we have now in that Newman projection? It is now staggered. This explains the drop in energy. Not only have we lost the bond angle strain, but we've also lost that Newman projection eclipsed energy. So a lot of things change as we move through by adding carbons into our structure. Okay? We have the ability to do rotations when we add more carbons. Those rotations make it more stable to cyclohexane, and they start to make it less stable. Okay? These are all things that we're responsible for acknowledging. You might say, well, how would I ever know this? Because you built a model and you played with the model to see that those things happened. That's why we have models. Okay? So, let's bring back our different identical structural and stereoisomers. What is the relationship between these two structures? Let's see, do I have the, I don't have the thing right there, do I? You're like, oh, I don't remember the flow chart. You should remember, all you really need to remember is the first step of the flow chart, because there's a huge typo on this. What was the first step of the flow chart? Same molecular formula. Do they have the same molecular formula? No, because some dipstick didn't realize that there's 2 carbons at the bottom. So let's fix that. Okay, now do it. Now they have the same molecular formula. So now we can't get away right away at the end, at the beginning with a different. We have to start dealing with our identical structural and stereoisomers. Okay? So moving through our flow chart, what was the next step? Because you all have awesome notes on that, or you printed out the slides and you already have the flow chart there. Are they superimposable? Can I possibly overlay these on top of each other? Well, if I do it, all the rings overlap, the carbons overlap, I don't see the difference. Wedged and dashed. Do those mean different things? Yeah, wedged means it's coming at you, dashed means it's going away. If I tried to overlay those on top of each other, yes, that topmost carbon overlays perfectly. The bottommost carbon does not. If I flipped the top structure over, they would now both be going away. So when I tried to superimpose them, the bottom carbon would be perfect. But then the top carbon wouldn't. So they are non-superimposable. Okay, where does that take me? They're now isomers. But I don't give you isomers as an answer. I say structural or stereoisomers. Structural actually means structural isomer, by the way. So it's just being, well, that means it's stereo. No, you can't do that. How do you differentiate between structural and stereo? The atom connectivity. Okay. The first methyl group, doesn't matter which one, is connected to which carbon? It's a ring. It's always 1. Where's the next carbon connected? 2. 1 and 2. Do they have the same atom connectivity? Yes, which then means stereoisomers. Okay, kind of makes sense? Okay, we have an interesting feature that comes up with these structures that we also saw already. Are those structures the same? The new ones I just drew? No. If we follow through our pattern, they will come in at stereoisomers. Right? What did we say the relationship between those was? Cis and trans. The top one is cis because those groups are on the same side. Trans, the groups are on opposite sides. Okay? Look back to our ring structures. Now look at me. No. The methyls in the top one, where are the methyl groups located? They're on the same side. They are both up. That can be referred to as a cis structure. How about the bottom one? Trans. We can use the cis and trans wording to explain the relationship between any two groups, be it on a ring or in a double bond. Okay? So that can be nice. Cis and trans really only allows us to define the relationship between two groups. This top one is also trans. Didn't we just say that was cis? Yeah, because they were on the same side, right? Cis and trans is any two groups. What am I saying is trans? Hydrogen to that top methyl. Am I allowed to do that? Yes. Okay. Cis and trans is an ambiguous term. It typically, unless it's specifically implied, applies to the largest group. Okay. But it does not have to be the largest group. It can be any two groups. Okay? So we can get this cis-trans system coming out of this. Okay? If we build a model for our cyclopentanes and our cyclohexanes, okay, where are the models viewed for each of those two images? What do I mean? Well, this was a six-membered ring. Does that look like the six-membered ring that I drew? How about that? No. Where am I looking at this molecule to see that six-membered ring drawing? I'm looking at it from the top, or, interesting point, the bottom. Does not matter which direction I'm looking at as long as I define it with what I'm looking at. Okay? Same thing with the cyclopentane. But what happens if we attempt to turn it on its side? Do we get the same drawing? No, we see a different drawing, which means we have to come up with a way to draw those different drawings. Way number one, cheat by a stencil where somebody's already done it and just draw it that way. That works. Perfectly acceptable. Okay? Or learn how to draw chairs. These are the steps behind drawing chairs. Since it is something that I discuss explicitly in lab, I'm not going to walk through it stepwise right now, but I will go through it really, really, really fast. So black, two staggered, that's not black. Two staggered lines, up, down, done, chair. What? Yes, that's how fast it needs to happen. Right? It has to go fast. Okay? Different energy chairs. Okay? What do I mean by that? Well, now I'm concerned about energy. Because when I looked at ethane and butane, I saw different energies. How did I see different energies? What did I have to do to see that different energy? I had to use a Newman projection, which means I have this overhead view, that's lovely. Okay? I have the side view that's a chair. I will also have the end-on view where I have a Newman projection. The cyclohexane has an added bonus, if you will. Okay. The cyclohexane does not have one Newman projection. It has two, side by side. Two carbon bonds disappear from view. Those two Newman projections are tied to each other. So if we went through and tried to draw one, we would end up with one like this for just cyclohexane. Nifty. Pretty. Okay. If we did our little eyeball thing, there's our chair. Okay. If someone sat in the chair, just to make sure everybody's on the same page, there's a happy little face. Sit, there's a butt. There's some really long, what are those, thigh bones? I drew it better before, I promise. Okay? We would be sitting and facing towards the right. The other thing we'll add on this to make sure everybody knows, the bonds in front are the ones by definition that are coming at you. The bonds in back are behind, or the lines drawn up are the bonds behind. The lines drawn down are coming at you. Okay? So we've got a whole bunch of ugly stuff drawn on there. Doesn't look too bad.
Say that again?
The lines of our cyclohexane that are drawn lowest in our drawing are the bonds coming at you in the model. The lines that are drawn highest in our chair drawing, because it's a two-dimensional plane, are the ones going away from you by definition. That's how it works. Right? We then have our Newman projection. Our Newman projection showing it very nicely in the eclipsed conformation. We spend most of our time looking at the eclipsed conformation because the eclipsed that's not eclipsed, that's staggered, thank you. In our staggered conformation, because the staggered conformation is lowest in energy. Right? Were there other ways that we could have flipped or spun our chair with single bond rotations? Yes. Would they have drawn images that don't look like chairs? Yes. Why do we spend less time looking at those? They aren't in the staggered conformation. Okay? When we look at this Newman projection, do we really see anything special about energy? I mean, there's nothing really unique or different or large. Those are all hydrogens around there. There's not going to be a big deal. Okay? They're staggered, that's it. Okay? How can I make this slightly more interesting? Okay? Add something else to it. So in this case, I've added two groups. Okay? I've added an E and I've added an A. Okay? Random pieces. Okay? So it's the same chair, okay? But I've now added two extra pieces, substituent. Are those substituents in equal energy location? So if I made them the same thing, okay, a methyl, would I expect the methyl in red to be the same energy as the methyl in blue? Okay. This is again probably where Monday's like, yeah, I got this. And Wednesday's like, I have no idea what you're talking about. We just talked about Newman projections, right? So get rid of that one. Okay. I'm concerned about the relationship of this with the rest of the things around it in that Newman projection. What is the largest thing in that group after A? One of the CH2s. Okay, so I will call it a purple CH2, and I will call it a green CH2. Which of those two am I concerned about? The green one. The green one's relationship to the blue is what relationship? That is our gauche, awkward urinal standing. Okay? You're like, wasn't the awkward urinal standing where they were up on the right-hand side? That interaction can happen anywhere around the ring, because what can the molecule do? I can entirely rotate that structure. Okay? So that is a gauche interaction. How about with the purple one? Is it eclipsed? Good. Is it gauche? Good. Is it anti? No. Good. Is it staggered? No. Wait, there's another option? Yes, there's another option. For them to be staggered, they have to be attached to different carbons. They are both connected to the exact same carbon. It does not matter what sigma bond rotation I do, spin, flip, rotate. The distance between the blue methyl and my purple CH2 will stay the same. That relationship is irrelevant to the energy. It may be in a very similar location as the green one, but it is irrelevant because I have to recognize they're connected to the same carbon. That will always be 109.5 degrees away. It will never change. That is irrelevant to my discussion. So if I look at the blue one, I've got this gauche interaction. See if I can undo this without erasing everything. Come back, come back, come back, come back. There was our E. There's my CH3. What is its interaction? Okay, this time I'm not going to erase the other half. I'm going to make it more difficult. What is it in a Newman projection potentially interacting with? As a hint, they're colored. Is it blue? No, those are not in the Newman projection. Okay? The blue is in the other projection from the red, so not relevant. Okay? So I'm looking at the green and the purple. I looked at the green on the last one, so I'm probably looking at the green this time. Is that always true? No, so be careful with that. What is the interaction between those? Those are now on opposite sides of the Newman projection. That is anti. Are red and blue different energies? Yes. Which one is lower in energy? Red. I've now identified that the location that the red one is in is lower in energy than the location of the blue one. Okay. Because they are different energies, now what I want to do, I'm Mike, you're Bob. Why do we do that? We need a name. We have to attach a name to these. Red and blue would work, but then because I use too many colors, we'd end up recycling red and blue later on. So we need something more creative than red and blue. As a hint, E and A are starting to help us out there. The red one is kind of on the equator, if you will, of our structure. That one will get called equatorial. The blue one is kind of on the axis. So we'll call that axial. Notice the blue one is in the up-down plane. The equatorial is in the left-right plane. So that means if I took this molecule and rotated it 90 degrees, equatorial and axial exchange locations. If you rotate 90 degrees, equatorial's there, rotate 90 degrees, where would equatorial be aimed? On the up-down axis. That doesn't make it axial, it's still equatorial. It's all relative to that structure. Okay? So we have these two positions. The equatorial is more stable than the axial because the equatorial has an anti-relationship with the ring. The axial has a gauche interaction with the ring. Okay? So big old typo on that one, isn't it? Our lowest energy places, the largest groups in the equatorial. That was put there just so that you make sure to change your notes. There's our equatorial position. Okay? Take a look at our ring. Yeah, actually not that. Where I'm holding now is my methyl group. Where is the gauche interaction that we just talked about? To our ring, right there. So there's that gauche interaction. Oops, I dropped the molecule. Is there another Newman projection?
Yes.
Yes. Do you see the gauche relationship between my hand and my hands now? No, I don't anymore, because I'm not looking at the Newman projection where those are in a Newman projection with each other. Where's the gauche interaction now? It's the methyl and back, or the CH2 and back. Right. That is insanely hard to see. It takes a lot of practice to deal with that and see that with a effing model kit. Right? Use the model kit. The reason why I mention this is for a question that somebody asked about and was curious about what's happening within it. Every axial position has 2 gauche interactions. Why 2? Because there's 2 Newman projections from the carbon that has the axial. You just have to change your viewpoint on the molecule to find the other relationship. Okay? Takes practice working with, but it gets you there. Okay. What happens if we do a chair flip? Okay, we haven't addressed this one yet. What is the relationship between these 2 structures? Are they identical? So I just drew the exact same thing again. I didn't draw the exact same thing again. How do you know that? What do you see? What do you see there, Devlin, that you're saying those are not the same thing? Versus, everybody kind of see that? They're not exactly the same. Something has changed about it. Yet, if we look back to our labeling, the blue atom is still connected on the right-hand side to the carbon in front. The red atom is still connected to the front atom, sort of on the left-hand side. Well, it's on the left-hand Newman projection. So the molecule itself is identical, but yet something about it has changed because I've drawn something different. What was that change? If I rotate it 180, an atom that's in front, if I rotate in 180, right, my hands are in front of me, rotate 180. Where are my hands? They're still in front of me, but if we looked at the drawing, they would appear to be away from you, right? So I heard clockwise versus counterclockwise. Okay, I did clockwise, theoretically, I don't know. Let's do counterclockwise. Do you end up with a different system? No. No. What changed?
You flip the head. How the CHs are above and below.
See where this CH2 is located? Identify that CH2 in the other structure. What did I do? I pulled this atom down. At the same time, what did I do? I pulled this atom up. I did not rotate the molecule. I took that front atom that was down, front atom that was up, and what did I do? I pulled it down. I took that back atom that was down and I pulled it up. That was all I did. So I did a sigma bond rotation. Well, nothing should change if I do a sigma bond rotation. Do the red and blue atoms appear to have changed their locations? Yeah, in fact, the blue atom is now kind of on that horizontal axis. You mean like equatorial? Yep, that's why it's labeled E. And the red atom is now on that up-down, kind of like the axial. Yep, that's why it's called A. Every time we do a chair flip, your axial and equatorial positions exchange. Okay? They will not change their orientation up, down. Okay? The equatorial in the left, that red atom on the left drawing, is aimed largely which direction? Up or down? Up. Where is it on the right drawing? So that's mostly in that up direction. Right drawing, it's still up. The axial, the blue one in the left drawing is down. Where is it? Mostly down. You may notice that the mostly becomes challenging. The mostly was referencing which position? The equatorial. The equatorial is the hardest to nail down, so don't nail it down. Nail down the axial. The axial is very clearly either up or down. Once it's defined as wedged, well, if the carbons are all solid, that means that remaining position must mean dashed. This is why it's important to identify those four pieces. Okay? So, examples that we could go through and do. We don't have a whole lot of time right this second, so I'll run through and do one really quickly, maybe two. Let's do two. Cis-1,2-dimethyl-cyclohexane. And actually, we'll stick with the cis. Cis-1,3-dimethyl-cyclohexane. Okay. So the cis we now know means same side. We're talking about methyls. So for the red one, I'm going to put one at position 1. Doesn't matter where position 1 is. Most people start top. So there's top. Most people also count to the clockwise direction. There's 2. They must be cis. They cannot be drawn as solid lines because I already have 2 solid lines. Okay? So I'm going to have to use wedges and dashes. What do you want to use? Wedge. Most people use wedge. I don't know why, but that's what most people do. I think they're about the same, but right. So we've now drawn cis-1,2-dimethyl-cyclohexane. What does the question ask? The structure of the lowest energy conformation. Okay. Conformation means single bond rotation, which means Newman projections. Okay? We could go all the way back to the Newman projections, and that was painful, but what did we learn from our Newman projections? Where do we want our groups? Equatorial. So I could go through now and just place those equatorial. Okay? Where's position 1? It is again my choice. I have no idea why, but I find the easiest position on the far right. There's my first methyl. Right? If I look at the drawing that I've set up, I counted clockwise. So my second methyl needs to go clockwise, which would be at that weird, awkward middle position. Okay? I want it to also be equatorial because according to my Newman rules, it should be equatorial. So there we go, and I'd say, well, there's my answer. And damn it, I'd be wrong. Why would I be wrong? That one's pointing. This one's pointing down. Did I draw cis? Nope. What did I draw? Trans. I was asked for cis. I drew it in the wrong place. Now I have cis. Okay. For the other one, because we're out of time, that took way longer than I thought it was because I guess I talked too much. Sorry. Or slowly. All right, everybody agrees with that. I talk too slowly. I want to go equatorial and equatorial. All right. Equatorial, equatorial. Everybody see that? Are those on the same side or opposite sides? This one's aimed largely down. This one's aimed largely down. Are they on the same side?
Yes.
They're both aimed down. Yes, they are. Did I draw them aiming the wrong direction? Yes. And theoretically, I think I actually drew... No, I actually did that. Okay. Okay. So with that, we'll have to go ahead and stop.